So first of all, to do that, we have to import all the necessary libraries, and then we also need to import the training data set that was already provided by the hackathon, as you can see over here. We're also doing some inspections of the training data set to make sure there's no null values, no issues with the data set in general. And we did the same with the training data set, testing data set. And first of all, we needed to identify the target variables. So as you can see over here, we used columns in training set to see the check for missing values and to check for data types. So it's important to check for data types because depending on how the columns are categorized, it can have drastically different effects on the training of the machine learning model. And it's also important to check for skewness because having skewness also affects our training process. So as you can see, one of the things you could see here, like the target versus the count, there's definitely a big skew on the leftward side. That means the skewness is very high, so we need to normalize it. So we imported some other libraries necessary, and then we also started defining our targets. So first of all, we dropped the ID and the target because target will be the y variable, and ID is not necessary because it adds false information to the model. And we also identified the column types based on the data inspection that we did. So we separated these into two different types, categorical and numerical. So the categorical ones are the discrete groups such as region, equipment type, solar, yes or no, these kind of stuff. While the numerical ones are continuous measurements such as number of rooms, bedrooms, number of children, education, etc. So create the processing transformation. So this is to make sure that the skewness is taken into account. So what we did was we used a logarithmic transformation for the skewed data set, which helped us properly transform it into a more stable form of data that can be better understood by machine learning models because machine learning models understand normal data more better than other forms of data. Also, we tried training the model with a simple regression model. So this was just a regression model with a log transformed target. As you can see over here, this is the learning curve that was deployed by it. And we were able to get an outcome of it. But since we had log transformed the target, the MAE was also in a log transformed version of the MAE. So we have to turn it back into the actual MAE, which gave us an MAE of 9.3. So the first outcome was 9.3. So this is pretty decent, and it put us pretty high up in the leaderboard, especially in the beginning. But then we tried other stuff. So first we tried utilizing a auto ML called H2O. So this auto ML automatically scans for all different types of machine learning models and compares them and minimizes their error rates. So first it's necessary to prepare the training data to make sure it fits into the H2O frame, because if you just put it in, it might not be able to understand the data properly. So we need to identify the target and we need to identify the columns properly. So once that was done, we define and train the auto ML. So first we put a limit for 10 models to start. This is just to understand and see what outcomes that they produce. And doing that, it gives us a leaderboard. And then from the leaderboard, we got an outcome. We got an outcome of MAE 9.3, but this is a local MAE using the train test split that we created on the training dataset. But our real outcome will have to be compared on a testing dataset that's already provided by the hackathon. So after doing that, we created a prediction using the testing dataset, which we submitted to Kaggle. However, since we only got an MAE of around 7.8. We will try to minimize that even further. So how we did that is by trying different things. Um, so some of the things that we tried was, advanced feature engineering. So we tried doing creating like different ratios such as square footage per room and square footage per person and size age index. So creating such features could further help the model understand the dataset better. And we tested that out, and it worked, and it gave us MAE of 8.7, which was in the local MAE. So in the Kaggle submission MAE, it was even lower with 8.71. Um, and then we also realized sometimes our MAE was decreasing, but it wouldn't decrease in the testing data set that was provided. So that means that we were basically overfitting the training data set and it wasn't really generalizing properly. So again, we tried another AutoML deep search using the new added features this time. So this new added feature deep search was set for 20 minutes. This means that the AutoML had 20 minutes time to find the best models to minimize the MAE. And one of the best models we got was a stack ensemble model, which integrated 5 different other models such as GBMs and XGBoost. It had a log transferred MAE of 0.31, and again, we would have to convert that back into a normal MAE to find it out, but we just tried making a prediction and submitting it. So this proved that it did do well. However, there was also a decrease in MAE compared to the non-feature engineered one. So this also made me think that maybe this just added noise to it. So what we tried doing this time was doing our random forest validation of MAE. So after trying a random forest, we also realized that the MAE was much higher and it was actually worse than the stack ensemble model that we had previously. And we tried different variations of random forest, however, they all had pretty worse MAE outcomes. And now what we did was we did another H2O AutoML search where this time we did it with the original features only, but a deep search this time with the original features. So that means no engineered variables. So this also gave us a tons of outcomes, and which gave us with a pretty decent MAE of about 8.701. And then as you can see, 8.708 actually. So this means I thought maybe we can try a blended approach because the engineered approach seems to be overfitting the training data set, while the other approach of not including the engineered model seems to be underfitting the data set, where it only does great in the training dataset, but not so good in the testing dataset. So what we tried was a blended approach where we did a weighted blend of the two models. And this actually gave us a slightly lower MAE of 8.708. And we tried many different other models by tweaking the weightage and tweaking the features. However, as you can see, it didn't really do much better. And even after the deep search plus feature versus the final stabilize, they were almost the same. So as you can see in this visual over here. So we tried one last try where we combined all the different models that we had to see maybe if they would do better, and this was also done in a weightage manner. However, this did not work because it actually had a higher MAE. So this was the final code. It was a weighted blend of the deep search engineered model and the non-engineered deep search of the original model, which gave us a MAE of 8.708. And this was my final submission for the Kaggle. And until my Kaggle competition, I scored 11th on the leaderboard, and right now, after the Kaggle competition is finalized, I scored 19th, which I think is a pretty decent outcome.